Guys, welcome to this next video. We're going to look at chapter 12.9. It is titled Absolute Dependent Motion, Analysis of Two Particles. Okay, the basic idea is this. We have one particle that's connected to another particle via something called an inextensible chord, or it's a chord, but it's inextensible. Okay, go look that word up. Inextensible simply means that this chord doesn't stretch or compress as we apply forces to it, meaning that its length doesn't change, right? Okay, so what's the basic idea is we are trying to see how the one particle moves in relation to the other one. If that one moves down, what happens to that one? If that one moves down, what happens to that one? Here's another example, but more complicated. Don't worry about it. The basic idea is you've got a particle there, you've got a particle there. They are somehow connected via a chord, right? Particle somehow connected to another one via a chord. And if that one moves, how does it affect the motion of that one? If that one moves, how does it affect the motion of that one? Okay? So that's the big idea that we're trying to tackle here. How do we do it? Well, essentially, our first goal, okay, not the first step, but the first goal is to determine the total length of this chord. Okay? So try to get that in your mind. If I'm trying to relate the motion of the two particles, the first thing I'm trying to determine is the total length here, right? Right, there are my two particles. I want to see how that one moves in relation to that one. I need to determine the total length. Okay, so that's my first goal. First goal, I would say. Okay, but then how do I get to this goal? And we'll see why we want to use it like this. Okay, why we want this total length. Let me just try to zoom in a little bit more. No, I think that's okay. How do we get to this total length? Once we get to it, then we'll see why we want it and how we use it. Well, the first thing we want to do in order to determine the total length of this chord is we need to set up a reference frame or a fixed point or a datum. Okay, we want to set up our datum. Datum is just a point in your system that is fixed. It doesn't move over time. Right? This block A can move up and down over time. This block B can move up and down. But we want to set up a fixed point so that we can measure the position of block A and block B, right? We want to set up a fixed point so that we can measure the position of B and the position of A, all right? So we've chosen this point C here and D. These are kind of, well, essentially that's our fixed point there. And there is our reference point. There are those two lines. And from there, from this fixed point, we measure the position to the block. And that is our positive position, positive direction. What am I saying? Positive position. Okay? So remember that position is a vector. So if we measure from the reference frame to the block, that is our positive direction. So if this block moves that direction, it's a positive. If it moves in that direction, it's a negative. Similarly with this block, there's our reference frame. We've measured the positive direction to the block. Okay? So there we go. We are looking, remember, what's the goal? The first goal is to get a total length. The way we do it is we want to calculate the length of this. So we need to set up a reference frame, a fixed point. We define the position of block A. We define the positive positions of both blocks, A and B, okay? And recall, recall if you were in the class, that the position needs to be directed along the motion, the direction of motion. So this block is moving in this direction, right? So the position needs to be along that direction. This block is in this direction, so this position needs to be in that direction. Similarly here, this block moving up and down, so we have the positive direction going along this direction, Okay? And this block is moving horizontally. So our position A will be along this direction, the horizontal direction. Okay. So I think that's perhaps maybe I can just finish this off here. So then, how do we then calculate our total length? Our total length would equal that SA plus length of CD plus SB. Okay, so remember we're going for our total length. SA plus CD plus SB, and that's what we have there. SA plus length of CD plus SB equals our total length. Okay, so ultimately, guys, that is our first, not the first thing we do, but the first goal in order to solve these problems. Is if we're trying to find the motion relative to this motion, right, via an inextensible chord, the first step is total length. That's what we're trying to do. We're trying to get our total length. Now, why do we want to do this? Because if we want, say, the velocity of block A relative to block, I keep saying the word relative. That's a bit of a dangerous word, but the velocity of block A as it depends on block B. Then all I need to do is take this length equation, right? This is really a length equation. And I take the first derivative. I look at the change in this equation with respect to time, and I'm going to get ddt of SA, I'm going to get ddt of L, CD, and I'm going to get ddt of SB, ddt of LT. And what we notice is that these two, your LCD, the length of this little arc over here, and the total length do not change over time, so they become 0. So what we're left with is ddt of SA plus ddt of SB, which is just essentially the relationship between the velocities. Okay? So hopefully that's a good intro. I'll carry on in the next video. Cheers.